Okay, so this video is actually more of a prequel video for something that we're going to start talking about, which is projectile motion in rotating frames. The Earth rotates, and so we might be interested in knowing, does that affect the arc of parabolas? Does it affect their trajectories? And the answer is yes. And the main thing we'll be thinking about there is the Coriolis force. So what does that do to projectile trajectories? This video, however, is really just sort of getting towards applying the Coriolis force. How do we think about it? And mathematically, where does it come from? So here's the idea. Let's pretend that we're in some sort of rotating frame. I'll use capital omega to represent the angular velocity of my frame about some axis. I am thinking about the Earth usually, but it doesn't really matter. Let's pretend this is rotating around a particular axis, so one axis for now. And we're interested in calculating what the rates of change of anything is in such a rotating frame. And so I'm going to adopt a little bit of notation. It's not standard, but it works for me. I'll use capital D dt to mean the derivative of anything. I'll think about vectors, but really anything. This vector A is anything I want it to be. I am thinking about vector quantities here with respect to an inertial reference frame. So imagine I'm out in space, I'm watching this thing turn, I'm floating inertially. So capital D derivative will stand for inertial frame calculations, that quantity measured in the inertial frame. And then I'll use the normal lowercase d's to stand for time derivatives that are happening in the rotating frame. And it's just because I don't want to keep on writing these bars with i's and r's all over the place. And the key takeaway, which I'm not going to prove here, but if you're interested, you can go look at like a Goldstein or probably in Morin or some other classical mechanics textbook, is there's a very clean way to go between the two frames. And that tells us that if you want to calculate any sort of inertial time derivative, it's just the time derivative in the rotating frame plus the angular velocity of that rotating frame cross product with the thing you're calculating. So that's a nice result. It's kind of interesting how that turns out. We're basically just adding in this extra operator of omega cross to our time derivatives, which is pretty interesting. However, we're not really only interested in time derivatives. I want second time derivatives because I know that that's how I'm going to get things like acceleration. So let's pretend I have some general vector, capital A. It could be position, but it could be momentum, it could be force, it could be any vector quantity we want. And I want to compute the second derivative inertially in terms of second derivatives in a rotating frame. Okay, so let's do this together. I'll first start by writing my dA dt as dA dt plus omega cross A. So that just tells me if you want to find a first derivative, take the normal derivative and then take a cross product. Now I want to take the second derivative. What does that mean? It means I'm going to be taking the inertial time derivative of this thing we just calculated. Okay, each one of these things is itself a vector, some new vector. So I have to apply this rule to each of them as vectors. So for the first one, I'm going to take the normal time derivative, which really means the time derivative in the rotating frame, plus omega cross that derivative. So that's how I took the derivative of this first term. Now I've got to do the same thing to here. Now these are both linear operators, and they both, the derivatives satisfy the usual rules of derivations, the product rule. So when I apply this time derivative here, I've got to do it to both pieces. Let's write that out carefully. I said carefully. So that'll be the time derivative inertially of omega. I never said that omega had to be a constant. And then plus the inertial derivative of A itself. Notice in the product rule, I do have to do the sum of these two, and you cannot flip the order because these are cross products. So remember the anti-commutativity there. So I'm keeping the omega first and I'm keeping the A second. Okay, so now I've got to work these two things out using this formula directly. This first bit will pick up a d omega dt and then plus an omega cross an omega. The second term is just repeating what we have there. Okay, so there's a little bit of simplification that happens here because I do have an omega cross omega, and we know that omega cross omega is 0. Any vector cross itself cancels out. And then we can distribute this omega cross. This omega cross, this term does not cancel because omega cross omega is not in the same direction as omega. So I'm going to have a triple cross product there that I could possibly simplify if desired. Also notice that I have an omega cross dA dt here and then another omega cross dA dt here. So those are going to double up. And maybe I'll go ahead and write it up here. So like I said, we'll get 2 copies of this. And then we'll also get, I'll save that term for last. And then finally, running out of room and also tilting up to the right, I'll write my last term, which is this d omega dt cross A. Okay, so that's my general version of a second derivative of any arbitrary vector in the context of a rotating frame. Let's clear this all up, and what I'm going to do now is I'm going to specialize to the case where A is the position vector, which I'll just call R. It doesn't have to be the surface of the planet or anything like that, but let's say that my A vector is R. I'll go ahead and think of this term as being, well, the thing that goes into Newton's second law. After all, Newton's second law only works in inertial frames. But I'll write this one as the second derivative that we're usually interested in solving for. So let's go ahead and clean this up, rewrite it in terms of Newton's second law with R playing the role of A, or with A playing the role of R. Okay, so here we have it again. Let's go ahead and identify the net force as m times this inertial acceleration. And so thinking about it this way, but thinking that I really want to calculate my acceleration within the rotating frame. When we're here on Earth firing our projectiles around, we're in that frame. That's what we measure. That's where A is. So I really want to solve for this. So I'm going to go ahead and replace this with what I call A. I'll replace this with what we'll call V. It's the velocity in the rotating frame. And see if we can move all of these terms except for the A to the other side after multiplying by m. So that'll tell me ma will be my net force as measured in an inertial frame. That's the normal external forces, gravity, etc., minus all these other terms. And the ordering of the terms doesn't really matter, but I'll explain what each one is. Okay, so here they all are. The ma, the acceleration, effectively, that's measured in the rotating frame is the usual net force, but with 3 additional effective forces. Sometimes these are called fictitious forces. They appear on this side as though they're kind of forces, but remember, these are entirely artifacts of the fact that our frame is rotating, and each one has its own name. This term with the omega cross R is called the centrifugal force or term. Now, it's not real, it's a fiction, it's an artifact of the frame. Remember, Newton's laws only really hold in inertial frames, and a rotating frame is not inertial. So if your physics teacher has ever said there's no such thing as a centrifugal force, he or she is right, but it is definitely something that can arise as a happy accident or a convenient way of treating motion in a non-inertial frame if you have to work in it. And sometimes we do. This term is the Coriolis force. It's just as fictitious as the centrifugal force. And you can see that it only affects the things that are moving. So this one will be there no matter what, even if you're standing still, depending on your location. This one depends on your motion. And if we are moving through this rotating frame, this Coriolis force will tend to deflect. It's a cross product, right? And cross products tend to deflect. In fact, we can see it has a lot of similarity with something like a magnetic force because it depends on the velocity, but through a cross product. So deflection is typical of Coriolis forces, and we'll examine that in more detail. This last term is the Euler force, and it actually doesn't really matter for most of our considerations here on Earth because it depends on how quickly the angular velocity of my rotating frame is changing, whether speeding up, slowing down, or even tilting, precession or something like that could lead to an Euler force. But usually this d omega dt is super tiny. Omega itself is already small in a sense that we'll talk about later. So we often can either ignore the centrifugal force because it's got an omega squared in it, or maybe sort of fold it into this F in some sort of effective G. We'll see a little example of that later. But this Euler force is almost always completely negligible unless you're standing on like a tumbling asteroid where the axis of rotation is wildly erratic. So our goal now is to look at each of these in spherical coordinates with a particular choice of omega. We'll usually choose omega to define our z-axis for the rotational axis of the Earth. And then in a future video, we'll take a look at how these cross products all work out in a three-dimensional coordinate system like that. There are additional vector identities that can let us simplify this cross product, this double cross product. And we'll analyze projectile motion for objects that are fired on a rotating Earth, which they all are. And we'll see especially that if you're firing at high velocity, this Coriolis force can actually have quite a big impact. And in fact, there have been cases even in World War I, for example, where long-range howitzer shots had to account for the Coriolis force in the deflection of the shells. So that is coming soon.